Willkommen zu AI Talks Nagele mit Köpfchen von und mit Dr. Johannes Nagele. Der promovierte Neurowissenschaftler hat seine Liebe zur Forschung nie verloren und spricht mit den hellsten Köpfen über die neuesten Trends rund um KI. Doch statt Business Blabla heißt das jetzt Nagele mit Köpfchen.
Hello and welcome to today's podcast recording. Today I'm very happy to welcome Tabajara, who has some background in multi-agent systems. And the interesting thing about it is that, as some of you may know, multi-agent systems don't only exist since yesterday or since the rise of generative AI and large language models, but it's a quite old and sort of also naturally arising concept in the field of AI or smart systems overall. And so I'm really happy to have you here today. Thanks to take all the journey on you and be here with us today. I'm really looking forward to the insights that we will get, and maybe we will also be able to do some transfer from the academic world, so to say, into the business world, and see what concepts we can transfer from one to the other. With this, I would kindly ask you to tell me something about you.
Okay, so first of all, thank you very much for having me. It's a pleasure to be here and to discuss about this nice and broad topic, which is multi-agent systems. So you have already introduced me. So I'm come originally from Brazil, and then I started there my PhD work. And after 2 years, I moved to Germany, where I continued my PhD work at the Clausthal University of Technology. And then I continued my studies in multi-agent systems. In particular, I was interested in the coalition formation topic, in which we have a set of agents and they want to cooperate, and how we partition that set of agents in order to achieve the overall systems goal. And so this would be my background. I really come from an area in which is about multi-agent systems, and now we see a trend regarding, okay, how can we use also multi-agent systems, and so we have different agents, and how can we combine them with the new technologies that are coming. And so, for example, generative AI, and then we also see some new terms being coined, for example, from OpenAI, like agentic AI, and how all of that related to multi-agent systems, all the work that have already been done in multi-agent systems. So I'm very glad to be here and to share and discuss a little bit of this with you.
Yeah, very nice. I think some of the listeners will already be very prompted, so to say, by some phrases that you were using. Maybe one step back. You are a computer scientist, or what is your background before the PhD?
Yeah, so I started as a computer scientist, and then I did my master, and then I started also my PhD in artificial intelligence, and then moved to Germany and also studied artificial intelligence at the Clausthal University of Technology.
Okay, thank you. You mentioned already, I also mentioned multi-agent systems. Maybe to start out, let's first give some definitions. What are we even talking about? In your words, what is an agent? I'm specifically asking you because we may have slightly different perspectives on it, right? But I think it would be very interesting to know what is sort of a formal description in the, let's say, historical way, in the traditional way. What is an agent?
Okay, great question. So I think an agent, it's very a simple term that the multi-agent artificial intelligence actually came up with. So an agent, it's simply something that can perceive its environment, and then it can reason about these perceptions it got from the environment, and then act on it. That's all an agent is. It's very plain, it's very simple. And so we perceive, we reason about it, and we act
So you are also an agent.
Yeah, I mean, agents nowadays, they can impersonate a persona, so to say. So you can also have agents behaving on behalf of some user. That's completely fine. But yeah, so we perceive, we reason, or an agent act. And then the two other things that we can also talk about the agent's behavior, it's when it comes to reactive. So this is how it always started. So we want to have agents which are reactive. They are going to perceive something from the environment, reason, and produce an outcome or perform an action in the environment. But we also could have proactive agents. So they are no longer just waiting for some input, or for example, from the user, but we also build the agent's architecture in order to consider, okay, the agent is always trying to pursue something. So it's always trying to bring about something in the environment and try to achieve that. If you can think of specific ways, you can think like an agent always wants to keep the room cleaned. So that's a goal. Whenever it perceives that the room it's blocked in some way, or you can have a different goal in which you are talking about, for example, the battery level of an agent. You always want to have the agent proactively going after to recharge itself or to get another energy source. So those are the ways that you can represent an agent. But all of these, it's about just a single agent perspective.
Yeah.
And then the main challenge came when we started back in the 80s, is to think, okay, but what if we have multiple agents? And those agents, they more or less, they complement each other. So we don't have a single agent which has the whole set of skills. It depends on others. And so multi-agent system started studying the cooperation and coordination of those agents. So we want to achieve that. So we have a system goal and we want to bring that one about. And how can we bring those agents together? They might be have different set of goals. They might be conflicting, and somehow they want to decide whether or not they want to cooperate. And after that, how they're going to coordinate to achieve their goal.
Okay. I think we will spend quite some time on talking about exactly these aspects about agents, agentic systems, multi-agent systems, and collaboration, cooperation, coalition. But just to start slow, to get like a mental picture, you also already mentioned, for example, cleaning the room, just for our audience to be able to have something, you know, in their heads while we will discuss the upcoming topics. So let's take that as our base example, a vacuum cleaner robot.
Okay.
Yeah, that is, if I understood you right, in this definition is already an agent, and it has multiple goals. It has the goal to keep itself active, being charged enough to be able to work, but it also has the goal to clean the room. And now you already mentioned the cooperation of multiple agents. One thing, for example, that the vacuum cleaner bot has to do, it has to plan a route, right? Sometimes the perfect route may not be visible, let's say, from the sensor information that the robot has. Maybe it has some scanners to see the distances to its to blocking objects or something, to walls and so on. Maybe it has something like a mental map of the environment. But there may be challenges that could only be solved by trial and error from this agent. But let's say if my security camera in the room could talk to the agent, maybe it could tell it, hey, this time you have an obstacle there, and I can see behind that obstacle and know how you can sort of get ahead that one. This would be sort of a help that could help the vacuum cleaner bot to save energy and not drive around trial error wise to find its goal, right? Or to clean all of the room in that sense. So would that be an appropriate example for sort of a collaboration already from two different agents?
Yes, yes, it would indeed. And also we can think about this very same example you cited, in the sense of a centralized agent, like coordinating the other agents in the system, or a completely distributed way.
Yeah.
So from a centralized perspective, following on your example, you could have this security camera agent as being the centralized one because it has the camera, it can turn around 360 degrees, let's say. And then it could tell this agent, okay, so now the user had prompted us to do the cleaning. That's completely fine from the agent's perspective, but there is something blocking our way. So maybe you don't start from this direction in your route, or you just take another path. Another thing, perspective that we can have from the same environment is when we have distributed. So let's assume that we have two vacuum cleaners robots in this very same environment, and also the security camera. So once the user inputs, I want this room cleaned. So what can happen is the agents start a protocol and they can decide, okay, I'm going to do room A, the kitchen, the living room, and a single bedroom. And the other robot can also decide to distribute the tasks.
So even if they have the same skills, the same abilities, because they are the same robot model, so to say, they could still do some task separation. They could split up the task into a meaningful way that is helpful to save time and energy.
Time and energy, so any kind of resource. And you could also have the security camera coming and not acting in the environment, but providing feedback regarding the plan and saying, okay, but this particular path that robot A, let's say, has to follow, it's blocked. So it would be better if robot B takes over the living room, because for his way, it's free, and then it's a better solution for the overall problem of cleaning the apartment, the flat.
Okay. And so the coordinator that you mentioned, in such a scenario where I have one coordinator, the agents themselves can be relatively, let's say, dumb. Because technically the coordinator could give precise movement instructions, right? So all the intelligence could sit in the coordinator, which, by the way, usually in most of the setups we call it group chat manager or group manager. In our current LLM agent world, it's all about language, so it's the group chat manager. But it's also interesting to see in the actual conversations that they have that depending on how you exactly orchestrate and configure it, sometimes really the coordination happens on the coordinator side, but sometimes they start to coordinate themselves a little bit. For example, by specifically asking one of the other agents because they know that that agent has a required skill or so. So it's sort of a mixture between the two that we usually do in these very open setups, at least. But I have one question regarding the definition of agent, because a lot of what you said requires also some sort of memory. For example, if the agents figure out you do this room, I do this room, then this needs to be somewhere in memory, right? Because it could, so is a memory maybe also an element that one should always consider when talking about agents, so that it makes the agent actually being an individual given the current state of the environment and the history of the state, so to say.
Yes, you can think of agents also have this sort of memory, so it can be a persistent also memory in which it can record, for example, the past rooms it was assigned to. But usually we think of agents as a living entity in the sense that it's always updating its behavior, it's always executing. And so once it has started, it's going to continue running until something, for example, out of energy or some event happens, and then you have to take up where you left off. But yes, the memory and where you keep your beliefs and your current state of your program, it's indeed one part of it. It doesn't have to, because, for example, you can have reactive agents in which they perform in a sense of like they just perceive something, they just process that information and then stop. They don't need to record anything in memory or persist any sort of information. So that is really going to depend from application to application.
Okay, thank you. So maybe one question that people would have when they hear all this is like, what is different to the collaboration of people? Is this like, could we learn in social sciences from the work that you and your colleagues have done? Or could you learn from social sciences about how to orchestrate optimally? Or from things like game theory and similar, also relatively well-established fields. How much can we transfer the insights and knowledge about such collaborative systems from one of these fields to the other one?
Yeah, perfect. So this is a very good point. So in multi-agent systems, we take inspiration from humans. So from a single human perspective, and also from the collaboration between different persons when they want to achieve some goal. And we also use a lot of game theory techniques. We also use a lot abstractions to come up with abstractions which we use these concepts we have in the context of human relations. And so just to cite some examples, one of the well-known abstractions we have when modeling a single agent is what we call the BDI model. And so the BDI is mainly, the B stands for beliefs, D for desires, and I for intentions. And the main idea is this is inspired by how human works. So this is already some work back in the 90s, 80s. And the idea is everything that the agent perceives, it's going to keep in its memory as beliefs, so what it knows about the world. And then it's going to have desires, which are its goals. But desires are not things that the agent's committed to do, at least not yet, because some constraints in the environment might not hold. So for example, suppose that an agent has its goal to recharge, always be recharged. Don't let its battery be empty, otherwise it won't be able to move anymore. So it might have this goal, this desire, but its battery might be full. So it doesn't have to be committed to recharge itself. And intentions is what the agent is actually committed to do. And so we have this big set of goals, what we call desires, and then the agent's going to reason about those desires and say, okay, now I can achieve this goal. Because some desires, they might be also conflicting. Mm-hmm. So the agent has to decide, okay, I'm going to pursue this one instead of the other one now. And in terms, so this is one of the well-known architectures we have when we're talking about agents and how, for example, we program agents. And also we have some other very interesting topics, for example, theory of mind. So theory of mind is how we try to understand what the other agent is doing based on its behavior. And so we try to re-engineer, reconstruct its model based on what we are seeing from it. And this has some very nice applications in the sense of, for example, argumentation. So argumentation is another part of multi-agent systems in which we want the agents to collaborate, or maybe they have some protocol, and they maybe belong to different stakeholders. And so those two agents, they have to talk and to agree on complete on performing some particular goal. And so maybe when you're in these sort of argumentations, and just to bring in the concept, an argument, So it's basically based on the concept that the agent has about the world. And then we have a binary relation over those concepts in which we say that one concept might attack the other one. And so this is, for example, you say, okay, I can come to the office. And then another agent is saying, okay, you can come to the office. But the thing is, this is weekend. And on weekends, the office is closed. So I'm attacking your argument, that you work at this company and you can come to work, because I'm saying this is weekend and this no longer apply because of this. And so you have ways of track back and explain why the agents behave the way they are behaving. And so when we are talking about theory of mind, you want to use these also to try to, okay, but what are the beliefs? What does this agent believe? And why it's behaving like this. So you can have also these sort of techniques which are inspired from what humans usually have and how we think about each other and what we coordinate and cooperate with each other.
Okay. Maybe to just elaborate on this a little bit and explain, like theory of mind is, I think, a concept from psychology that came up mid of last century or so. I'm not sure actually, and I also forgot who exactly invented it originally, but I think it's a quite natural concept. Probably people were already thinking about that 400 years ago. It's basically saying that in order to cooperate with others and interact with others, even with animals or other entities in our environment, we sort of build mental models of how these systems work and would react to certain inputs, to certain stimuli. And I think even you can say, or I think it's evident nowadays that we also have a mental model of ourselves, of course.
Yes.
So you also have an expectation to what happens when you let your arm fall, right? This is a mental model. You sort of can be able to simulate through the behavior of not only your body parts, but also to some extent, depending on the experience that you have with the other system, but you can also simulate in your head what could happen if I do this or that to the other person, to the animal, to the vacuum cleaner robot or whatever. Yeah, we have ideas of what could happen. And I think this is a very fundamental concept. I think also what is maybe important to mention about it, there's also neural evidence for this. The concept of mirror neurons or grandma neurons, I think, is very well known. And there's also evidence of things like if you have a very strong model of another person, maybe you know it from when you interact with your kids or with your partner or so. Sometimes it happens that you can sort of feel the pain that the other one has. Right, when you observe someone hitting itself on the corner of the table or so, then often it happens, like at least to me, that I'm like thinking myself, oh my God, shit, I'm expecting some pain. The pain is not coming, but it's clearly a sign that my model was already inferring that there will be a pain, at least for the other person. And I think I could talk very long about that concept because there's many interesting aspects about it. Also with like how the hormones react actually, because if we observe others doing things, even our hormone system reacts to it, which is also part of this mental model of the other person. And even if you observe, if one animal observes another animal of that same species moving around, even the cognitive map is being activated that sort of does the navigation part, and sort of you are co-navigating with the other one that you are observing. That's quite interesting. There's really evidence for this. And I think what is important to mention that it's really helping the coordination, right? This is, I think, the crucial part, that when you have an understanding of how the other one might react to a certain input, to a certain situation, that allows you to plan your actions. Because if you want to have the other agent performing something that pays on to your goal, then you need to know how to trigger it. And how to need to know how to trigger, you can either achieve by just doing a lot of empirics and just trial error over time, and maybe just memorize the best action in order to get the other one doing what you want. But you can also only collect a limited set of empirical memories, so to say, and use that together with the world knowledge that you have to build a global model of that other person. And then you can refine it over time. If you figure out, okay, my model was not perfect, in reality the other agent reacted a little different or so, you can sort of refine it over time. And I think that's pretty much what also happens throughout our lives. And that is also an interesting part that we see for AI agents, because we can continuously feed learnings in. So we call it also active learning. It can also ask even the user, hey, was this good what I did? Or do you want to have it differently? And one agent can also ask the other agent, for feedback. And so I'm already jumping a little bit now in the AI agent world. I will slow down on this because I want to learn more about Tabajara's work on coalition and so on. But just to mention, so we had some previous episodes on multi-agent systems and some webinars, and also a lot of blog articles and stuff. So there's a lot of background information about that available. Feel free to check it out. But to just revise this a little bit here, so Tabajara already mentioned very nicely what an agent is. Yeah, what is the definition? And there was also the part of the intelligence, the cognition, in order to be able to do something. In the human case, it's our brain or our nervous system, yeah, that allows us to process information and decide what action to do. In the world of AI agents nowadays, what is called AI agents in these days, it's typically a foundation model in the background. Typically a language model, because that is the kind of AI that is easiest to access and easiest to steer, so to say. Technically, it could be any sort of algorithm in the background or any sort of classical machine learning model, or whatever sort of cognition you could imagine. Yeah, if it's even, it could technically also be just a simple if-then-else statement or a mathematical statement. Always add up all the numbers that you get as input, and you would be the summary agent, so to say. But the interesting part, of course, is when there is some sort of real intelligence, and I'm putting this into quotation marks, of course, because some people will immediately jump off their chair when I say real intelligence and talk about large language models. But it's definitely a stage where we reach now in terms of intelligence that is far beyond what we had like 5 years ago or so. So people are now really, and important people are now really discussing whether this is already AGI in the sense of artificial general intelligence being such an intelligence level that it, at least in many tasks, already reaches human level performance. This just as a background. So this is the world where I'm coming from currently, these large language model based agents, but the concepts, at least to my understanding, pretty well align. And so in the essence, we are talking about the same thing. But the studying of it is much more, let's say, structured in your research work than what is happening right now in the AI LLM agent world. I feel like there's the best practices and all the sort of boundaries or the criteria, how to set the parameters, how to set up teams, how to set up multi-agent systems, maybe do it hierarchically or not. These are all things that are being slowly developed, but the very, very crucial and interesting part, and also the reason why I think we are talking today, is I'm so puzzled by that we are not using these concepts that have been there in other science fields and apply them, because I think it's possible. So yeah, maybe we can take this as a point where we jump a little bit more into the coalition part, the collaboration part of the agents, and the way how you actually are studying it. Because what we talked so far was quite, let's say, high level. And I'm sure that some of the people listening would be like, no, yeah, but how? If you don't use language, how the hell are you telling the agent what to do? Or what is a belief for a agent before you could like prompt it to believe X, Y? Yeah. So if you cannot just prompt this, how do you actually do it? And how do you study those systems? And maybe then you can also talk in that context about the multi-agent programming contest that you have been participating also, because I think that is quite interesting also to hear about. Yeah.
Okay. Yeah. So many things that we can talk about there. I think that's an important the topic that you pointed out, also to connect to what we were discussing about multi-agent system taking inspiration in other fields of science in general. And I believe this is also a contribution for multi-agent systems to now this part of deep learning and generative AI, in the sense that, okay, look, multi-agent systems has been around for a long time, and it has defined, and we are very good actually at this part of concept and abstract levels. So we have very good researchers who work on this part, and they come up with a very nice concept and how the system should work in the abstract level. And so this is a way of saying, okay, so you can just use all this knowledge. It's already out there. So we took inspiration in social sciences, for example. You could also now take inspiration in social sciences, and also taking a look at what a multi-agent system field has delivered in terms of contributions to this part of artificial intelligence. I think we have a lot there that we can try to discuss and integrate. Actually, that's a very nice period of time for researchers in multi-agent systems, because we have these low-level techniques that weren't available back in the 2010, for example. And then now you can integrate them. So you have very nice abstractions in the multi-level, and now you can have very nice tools in a single agent from a single agent perspective that you can use in order for your system to maybe improve the performance of your system in general ways. So I do think that we have this correlation of different fields, and they could work very nicely together. So basically, one of the topics that you pointed regarding the multi-agent programming contest, so maybe this is a very nice topic to talk now. So this dates back to 2002, when we had different research groups studying multi-agent systems, and of course, what you want to do is to evaluate those systems. So just to bring a background, how it was, multi-agent system was back in the beginning, back in the days, used mainly for simulations. So we wanted to deploy simple agents, so for example, reactive agents, to study biology. So you would have your agents represent some specific animals, and you would input their behaviors, and you wanted to understand if emergent behavior would come out of those individual entities. So multi-agent system has been applied a lot in this background. But now I have developed that we can do much more. And that's where this agentic AI is coming, in which we want now to give to our agents the goals I want you to achieve this. Or I don't really have to specify all the sub-goals. I can give just the general goal and allow, and this is an important part, allow this agent to decompose those goals and act on my behalf to achieve those sub-goals. So this is a part of the... I would say even that this is our current state where we are at the moment. So we have big companies working towards this. So for example, OpenAI, which is working on agentic AI. We also have a very interesting project. So for example, if you Google Auto GPT, you're going to see the first, an attempt of how you can use that. So you would just provide an overall goal, abstract goal. Okay, I want to plan my birthday party. And then this agent would decompose those tasks. And for example, check if you have everything you need in terms of snacks, or prepare a snacks list, and send out invitations to your friends. And so it can decompose those overall goal, and then you start on working towards it. That's a very interesting topic.
Okay, to go one step back to what you said, you mentioned biological systems and basically simulating biological systems and checking for emergent behavior. Very interesting field, I would say. I'm thinking of the game of life, which is like from Conway, which is basically using cellular automata to also simulate emergent behavior. You could even say each cellular automata is in a sense an agent, right? I remember back in the days when I think during my master's studies, I studied biophysics, and I was lucky to be able to work in the field of computational neuroscience back then, and I gave programming courses for students. And usually you always had like these plans of you introduce functions, you introduce variables, you introduce and so on, and then maybe have some examples. We tried a different approach because those were biology students, and I wanted to be as least try or as possible. It should be like tangible for them. So we voted on what we want to do. And then we decided, the decision was, we are going to simulate a Lotka-Volterra system, which is basically a dynamical system, an ecosystem between, in this case, we used mice and cats.
Cool.
And basically have them being running around in a 2D environment. And when two mice met and they had the right gender also, then offspring could happen. And the same for cats. But if cats and mice get too close to each other, then there's a certain chance that the mouse is being killed, a very, very low chance that the cat is being killed, and so on. Yeah, and it was quite nice to see that there was no emergent behavior happening. But it was really nice, and also for the students, I think, to see that when you set up this simulation by really heuristical rules that we just came up with, we didn't look anywhere online or about production rates or something. We just came up in a playful way with it, and then in the end, when we simulated it and looked at the population numbers, nicely the Lotka-Volterra behaviors showed up, and we could even fit the actual theoretical formulas to that, and it just fit perfectly. And I like this story because it clearly shows the connection between theory and simulation, or practice, if you want. It's still a very theoretical environment, but so this leads me to the question that was in my mind while you were just talking about the ways how you sort of or what the research can provide. I'm wondering, on the one hand, you have simulation. You can try out, right? You can do an educated guess, maybe take some input from social sciences or so, and come up with educated guesses, how to set up the agents, how to set up the beliefs and the desires, and the, what was the last? The intentions, yeah. But is there also a theoretical framework in terms of equations that would give you maybe some boundaries for that, with some limits, for example, something telling you, okay, no matter how well you design your agents, you will never reach beyond that performance, or something like this? Or, for example, rules in the direction of, are you going to have more success if you have an army of agents that have all the same capabilities? Let's take like an ant state or a beehive or something. Or do you want to really split the abilities as well, right? So do you want to have, we could also maybe in the business world, you would call it vertical and horizontal skills. So is it better to have one general agent that can do a lot of different tasks and then you on the fly adjust the tasks? Or is it better to have like really, and a group of such? Or is it better to have really specialists, which then, together achieve the goal? Are there some rules like this? Is there something that you can derive on paper with math from some basic assumptions or so?
Okay. Yeah, I mean, great question, because it's a very complicated topic. And I'm afraid that I have to say that when you're talking about do we need more specialist agents? Can we have generalist agents? It's a very tough question, because when you're talking about distributed systems, it's so complex because we have different states. The agents might be in different states. That I'm afraid the only way that you figuring this answer out is by trying. So that's where you have simulation, which plays a very nice role. Yeah. So you can just, okay, what if now I have one more specialist agent? How would the system behave? And then it starts behaving much better or much worse than you had expected.
I think maybe an answer to this would also be that, why do we even do this, right? Because we want to solve very complex challenges. And complexity requires separation of tasks, usually, in some or the other way, to deal with this complexity. But the complexity of the problem itself makes it clear that we reach a limit with normal equations, let's say, with an equation system to model this. So it's really more about simulation, as you say. I think this is the only thing that we can do, and we see this in practice in our projects as well, right? We need to really try out. We can also use the intelligence of the agents themselves in order to make suggestions how to try out and so on. But in the end, it's trial and error. It's seeing, it's like press the play button, check what comes out, and then optimize it by that. So optimize the simulation over time.
Yep. Maybe another point that I may add is this trying to figure out what is the best setup for your system. It can also be, we can also do this in the context of agents if the agents can adopt different roles. Yeah. And so the agent can figure out, okay, I'm a specialist, but I haven't received many tasks to perform in my specialized area. Yeah. And so if I do have the skills, I could adopt a different role in this organization. Yeah. And so this is a very nice topic because usually when we think about roles in multi-agent systems, what we think is we have role A, B, C, and they're based on some set of skills. If the agents have this set of skills, they can adopt that role. And so, but it might be the case that we want an agent to only adopt a single role in our system, don't allow them to play different parts because we have enough agents to do that. And then we can play around with that and let the system itself to kind of find its way in which it improves performance. So that's also a possibility that I just want to add.
This is very interesting. I think this is a very, very crucial area of the whole discussion. And I think it will be the future of how we design systems will be there will be a lot of discussion about exactly that. How horizontal or vertical you want the agents, how specialized or not, how much resilient do you want to have your system? Because if one in the world of where everything only happens in a, let's say, on a software level, of course it's no problem usually that you don't have a chance that one agent just dies out, so to say, or disappears in the system. But as soon as there will be embedded systems on edge in like really robots and other IoT devices or so, then it starts to become a problem. If one doesn't find the charger and the battery is out, then this agent is out of the system. So if this was the crucial specialist for the task, then you have a problem in the system in case the other agents are not able to adopt and to take over that role to some extent, maybe in a shared fashion. Maybe one decides to do this or instead or so. So I think actually when my colleagues ask me, yeah, but how do we now design the system? How do we decide what AI model we use for the agents? My answer is, or I would say, the design principle behind all that I see is that you use the smallest model, the most energy saving model that you can use in order to still acquire the goal. So you take the least capability, because then it makes it also more controllable. It consumes less energy, and it's just slimmer, also faster. Usually you have lower latencies, but just add a little bit of buffer on top, so to say. Yeah, so I would say it's like if you have an engineer being trained in a very specific field, working for a manufacturer for 30 years, you know, at the beginning of the career, it starts out as a how to say, a generalized specialist. Yeah, so it learned field of engineering, but there's still room for specialization throughout the career, right? Yes. And then in the end, if you have a very specialized engineer in your team, then to change the role, it's a little hard, but it can still be done, but it requires some retraining, right? Because of course the behavior gets more and more specialized over time, and the ways how you act are also becoming more and more rigid, I would say. Yeah, because you found out your personal best practices and you follow those, and when someone tells you now you need to do something else and use different best practices, you need to adopt. But we still have this ability, right? We still can do this. Even up to the really high age, we can adopt a little bit. And I think this will be also the core for agentic systems, that we design slim systems, but still give them the chance to, at least to some extent, take over the role of another specialist. So it's sort of in between vertical and horizontal skill sets. But it's very interesting because we are also thinking about when we build a specialist agent for one industry, how do we need to design it in order to be able to reuse it in a different industry? Of course, you need some extra configuration. You need to tell it the new context. You need to sort of do the Umschulung. Yeah, the question is, what is cheaper in the end in a special case? Do we build very specialized systems with agents that are really specialized, or do we build multi-purpose agents that you can reuse again? And one way how I was actually also modeling, because you mentioned the simulations, how I was modeling this lately together with ChatGPT, by the way, and I made it crash. It did just not respond anymore because the simulation that was, I think, a little too complex that I asked it to do. So we were talking about biology already, and there's the concept of epigenetics. So basically, you can sort of modify the way how your genes are read out throughout your life, based on your experiences. This is a very interesting concept because it changes the way how we see evolution quite a lot. Because this way of how your genes are read out can also be inherited to your offspring. And then we have memes. like we have cultural genes, so to say. We can talk to each other. Agents can share information with each other. And successful behaviors could then, via epigenetics, so to say, be implemented in the long-lasting behavioral rule set. So in the long-term memory, if you want, in the skill set. And together, these concepts, I think, are really powerful for agentic systems. But in order to play around with all this and in order to optimize these systems, I think one very important aspect that we didn't talk about is the evaluation and like to give value to the individual contributors to a system, right? So if I have a team of 5 specialists working together, or a team of 5 generalists working together, or a team of 20 specialists working together, how do I actually measure what was good in the end? Of course, I can look at the overall accuracy of the goal, whether it was solved, how often it was really solved or not. But then I still don't know, was that one agent useful for achieving that goal or not? Or could I, from the 20 agents that I put there, can I maybe just remove 15 and it's still the same performance in the end? So as far as I understood you in your work, you also were looking into this part of evaluation and attributing value to individual agents, right? I find this very interesting. Maybe you can elaborate on this also a little bit.
Yes, of course. So this is also a part of a very nice topic, because when we are thinking about cooperation and also coordination, they occur, and once the coordination, how we achieve the tasks are done, usually we have to split the reward. So usually when we achieve a goal, we're going to receive something for it. And this is one part in which multi-agent system has used a lot game theory. So in game theory, we studied this sort of which techniques we can deploy and we can use to kind of split the reward within a set of agents in a way that the ones that contribute the most can receive their reward. And just to give you a simple example to elaborate on this concept, you can think of prior to agents joining a coalition, they could have the goal, and they could, okay, for this goal, I can achieve 2 tasks of this goal. And another agent might say, I can achieve other 2 tasks. Another agent might say, I can achieve 1. Okay, then we have 5 tasks that we can achieve, so we can form a coalition because we know we can do it. And this you know up front. So you have the agents kind of establish a value for that goal they want to achieve because they can contribute toward that goal. And once you achieve that goal, usually we're going to have the reward. And game theory comes and say, okay, if you want, we have some very nice properties in game theory, for example, Pareto, and another properties that you want your algorithm to follow. Mm-hmm. And then you can just say, okay, so this is the optimal way that you can split the reward based on the bits that those agents did. And of course, you also have to stay in the loop because just because you have agreed on a plan doesn't mean that in practice, everything is going to go smoothly. So it might be the case that another agent has to take up other tasks, and then we're just adding complexity on top of that. But that's also part of distributed systems and real world, really, because it's complex, it changes, and the environment is completely not observable entirely. So new things are always coming.
Like what you just said about the game theory and splitting the reward onto the different contributors, this is very interesting because it really reminded me of a very commonly used principle in explainable AI, where you need to contribute value to individual features that you are using. If you want to understand which feature did actually lead to that result. If we have a black box model, we want to understand what feature had what impact. So basically, we are applying the same principle here, also taken from game theory. So I always like to see these, connections between different fields, across different fields. It's very interesting. But also to bridge it a little bit now, also make a connection to the business world. so these frameworks, these concepts that you were describing, I think what is really nice about that, and maybe that is also important for many people that come more from the business world, is that this value is also, you can link to a business value, right? Because you use the word reward, the outcome is, you can link it to KPIs, or you can link it to just money saved, for example, or extra money earned, or something like this. And then if you do this properly, you can in the end transfer back part of that reward to individual contributors, to individual agents, and say, okay, this agent has a business value overall because it's used in this and this and this use case, and it has from this use case that contribution, from this use case that, and from the third one maybe no contribution because there it was useless. But you can sort of sum up all these reward values and then get something like a business value of that agent, and that can help you to manage, to govern the whole swarm of agents that you have, yeah, because at some point you also need to maybe remove some of them because you have limited resources and so on. And so this principle could really help you in that. And to bridge back again to biology, I think that's also what is actually happening in cells with proteins. For example, there's also like a garbage collection system acting, so to say, which looks which proteins have, I don't know, are not working properly anymore. So they are being dismantled and removed. The resources are given free again for building new agents or new proteins in that world and so on. So what I learned today is really that there's a lot of potential, and it's probably really worth to really talk more, connect more across the fields, across the different research areas, and also to industry, and that there is a high chance to really get some fundamental best principles for designing agentic systems. I think we could talk forever. I would have so many questions also about hierarchical coalitions and so on. So basically teams of teams of teams in this world. Also open teams, it doesn't need to be a rigid team structure, like in real world, right? But I think we have to sadly stop at that point. Maybe one last question. Yeah, we are already over time, actually. But my question to you, maybe a more personal and philosophical question, would be, where does all this lead to? We already talk about agents as very similar to how we talk about human. We often also draw this example, or like used human as a metaphor for agents. I think some people may be scared when they listen to this. Like, will agents be the next human, or will we augment us with agents? What do you see happening?
Yeah, great question. And I do think that we are in such a exciting time, because we see these artificial intelligence techniques available to us and users to be able to communicate and to interact with. And I would say it's scary, of course, because we haven't been raised in this kind of environment. Of course, the newer generation, for them, it's going to be like piece of cake, just interact. It's no issues there. But for us, with different backgrounds, we usually, the way we interact with the system is just, okay, system, do that. Okay, see the output. Okay, now do that. And this is sort of changing. And I think this agentic AI, it's coming for this. What I do see, and I would very much expect from the new technologies coming in the next years, is that as we have for some softwares, not all of them, but some, we really want the software to have some properties. So we really have to, for example, in safety systems, we need that. So it's not there's no room for discussion. We need those properties. And I also see this coming for AI, generative AI. And what I really wish to see is the integration of those. So if we're talking about multi-agent systems, we have already, agents are mainly based on logic, so you can infer formal systems and show that the system delivers some properties you expect. And so I really wish for this union so that we can have generative AI or agentic agents, and they come until a boundary in which they provide the input to these systems in which we want to protect, we want to deliver given properties. And then the system just behaves as we designed, humans designed, and make sure that in the formal way, in the mathematical way, it's going to deliver what we expect. So I do wish for this, and I see it coming in the future.
Nice answer. Thank you. Just one last follow-up on this, because I think it's really important to mention exactly what you said, the safety. I think that is a good argument for multi-agent systems, where each of the agents has a limited capability set. Small entities are much better to control, right? And I also personally feel it's like more natural to interact with like limited capability systems, as like I'm not so used to talk to a big god that can do everything for me or give me the number 42 in the end or something like this. So I think it's, at least personally for me, it's a much safer feeling when I have I don't know, a swarm of ant-like agents in front of me, as like this super big AI that would be able to do everything and does everything. Yeah, I think we can more easily switch individual elements of a multi-agent system off in case than it may be with this master AI, let's say. But yeah, maybe if you have some last thought on that or anything else, or if you have some question, then you can use this chance now.
Okay. Yeah, I think this is a great topic. I also feel like, okay, if we are talking with some limited agent in terms of capability, it's also something that we feel more comfortable with. I'm not entirely sure about the next generations. Maybe they're going to be completely fine with that.
True.
But I do see that these new technologies in the very sense for the future, they're coming to assist us.
Yeah.
So that's the main point. So if you're out there, you're scared about artificial intelligence, I would say they are coming to assist us. Also, government agencies, they will make sure that they are coming for this purpose. And they're going to regulate, they're going to specify what's the intended idea and usage of those technologies. So I would say get more excited about starting using it, starting playing with it, because you're also going to see, okay, this can help me so much. And then we're going to have, of course, to think about the safeties, how we prevent the system to do some harms. But all of this is coming. And yeah, I would just wish you to play with that and have fun with this.
Thank you so much.
Okay,
Thank you so
welcome.
much for being
very
here.
Nice to be here. It was a very nice discussion.
Yeah, I liked it a lot. And I would totally underline what you said. Yeah, let's see also what will be the interfaces between agents. What will the governments do in order to have proper protocols? I think we all need to be actively working on it.
Yes,
and there's no one that can decide all that alone. We all, also the users, also people trying out the systems, as you said, we all can contribute in order to get experience and develop this further.
Yeah. So
thank you so much.
Thank you.
Goodbye.
Bye-bye.